Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will talk about materialized views in terms of query processing and optimization. We will see that how we can perform the view maintenance on query and then the incremental view, the view on every operations like this join operations, set difference operations and other arithmetic operations, comparison operations, and then finally set and complex operational on the maintenance on a materialized view. Materialized view supports give us a view that is stored inside the memory. When we talk about view, we know that we are actually taking a partial value on a relation. That means every time it is not needed for us to go for a relation at a whole. So we need a particular portion of that relation for our computation. So we create views in SQL or other query language so that we can have a better look and a broad look and a relation only have a part of it. Now what happens that these views are a conceptual process or a conceptual basic. So when we are talking about a conceptual or logical one, that means the view is actually not stored into the memory of a database. When we create such views, we are actually having the view of a particular relation. So when we are updating or inserting the view, that means we are inserting only to the part of the relation. So it is logically not possible to update a view because we cannot just have the view on a relation that is not being updated, but the view is being updated. Say suppose instance that a rival relation instructor has the ID, name, salary and that department. Now we have created a view on the ID, name and department of that particular instructor relation so that one person can have a look at the view of an instructor without viewing his salary. Now what happens if we just update the ID and name of a particular department on an instructor? So the salary of say 50,000 of an ID 101 named Kim, department physics, has now belonging to 101 Kim, chemistry 50,000. So the view and the table has got two different levels other than if we update perform on the view, not the table. So every time we need to perform the update, we have to perform it into the original relation, not the view. The view won't be automatically updated. So logically, we can only insert and delete, not also a delete, but a modification on the view, but the updation is left for the relation. Now, if there is any need, say for the large databases, we need the views regularly or for a regular purpose. Then we can store this view in the database management system. Now the DBMS not only now stores the view as a logical one or a virtual concept, it also stores a view into a DBMS memory that is known as a physical view or a materialized view. That means we are creating materials on a view. Now suppose that a relation department and instructor is as follows. It is containing the department name, building and budget, and ID name, department name and salary for the instructor relation. Now what happens when we create a view on this joint relation? So we can just create a conceptual view as well as a materialized view. The creation of a materialized view is just same as the conceptual view, but it will be stored into the memory. So let us first create a view on this instructor and department so that the view will be used to create and update the total salary of each of the department that we can have. That means the view will consist only the salary and the department name as a part of this joint relation. So it will create a view named department total salary, which will have two attributes, department name and total salary, from the instructor relation, that is department name, and the salary is calculated as the summation of salary group wise of a department name. That means we are first grouping it by the department name, then we are calculating the sum of the salary as the view. So now if the instructor relation has So if this is the view of an instructor relation, then we can have the view of an department total salary as so there are mainly 1, 2 and 3 departments. So I am grouping it down by the physics, chemistry and the maths department. So now the physics department's total salary is 1 lakh. The chemistry department is 1,10,000, but the maths department is 20,000. So this is my view that we can create out of this instructor relation. So now if the materialized view, it will store the department name and the total salary on the instructor relation. But the main problem with the materialized view is whenever there is an insertion, deletion, updation to the relation, we need to keep it update with this view too. Now if the view is not updated that we are storing, now we are performing some functions on the view where the actual result in the relation or the values in the relation has been updated, then the view will be an erroneous view. So the materialized view need to be kept updated by time to time to support the instructor relation or the main relation that it is referring to. Now what is the use of this materialized view? Say suppose that we regularly want to update the view of a physics, chemistry and maths department. That means the monthly or the year-wise salary or the increment on a particular department. So we can easily have that from this view other than looking at this instructor relation where we have to calculate each time the aggregate functions. Now the aggregate function is a part of this view, and we can just perform the aggregate on this total salary each term on the particular relation instructor to have the total salary department wise, monthly, regularly or yearly. So in this way the view maintenance is absolutely important. So the view can be three typely maintained. First, in the incremental view maintenance. Incremental view maintenance is happening that if there is any update, then we will maintain our view according to the update. Now this incremental view supports both two types. One is an immediate update. If there is any update at that point of time, the view will be updated. Another is a deferred update. That means we will hold the update for the relation and then for a particular period of time after that we will update our view. Say for we want a collection of data that is after 1 day or at the end of 1 month, we want the result. Say for an inventory maintenance of a particular product. So it can happen that within a day the relation gets upchanged quite a lot of time. But we do not want that update on the view because the view is having on some purpose. So if we are having the view for the inventory calculation on a monthly basis, then we may want the update on this view particular at the end of 1 month or at the end of 1 day. So then we can use the deferred update, or rather than in situations that we want every update to be updated on the view. Now to use the immediate update of view or the deferred update of view, both of which will use the process of incremental view on maintenance. Now how we can incrementally maintain a view? To incrementally maintain a view, we will need some simple operations first performed to it, and then after the simple operations have computed with their result, with the result as the input, we will perform the complex operations to it. So first we will discuss each of these operations that we can perform to actually perform the incremental maintenance on view. First is the join operation. On the join operation, we will talk about the insertion and the deletion. Say suppose we are joining two relations R and S. Now we are referring to the values R old with the tuples on this old relation R and the new that is being updated with the R new. Since we need maintenance on view after only is there any update, that means we are choosing the updates only. So R new is an imperishable part of this view maintenance. So we can refer to the value old referring to or R old related to S. Just like the same R new with S. Now we can say my R new is the R old with the S that we have joined with the new R new. So how we can refer it? Now if we say that IR is the insertion or the updated value that we want to make on that particular R old, then we will join that value first and then we will join that with S. So now my V new will be replaced by this one, that is R old joined with IR, that is the insertion to this R old value, and finally joined with the S to have the value new to it. So how we can perform the insertion? We will just add the inserted value joined with the previous values on the relation and then the value on the relation that has not been changed joined to the previous relation. So for the same S, it will be happen with IS joined with S and then we can have joined with R. Now how to delete an operation or a particular tuple from this relation? Just delete the tuple from the relation with the set difference operator and then join it back to the new relation. If dr is the value that we need to be deleted, then my v new will be v old, all the value from this old minus the dr joined with s. That is every tuple that has a relation with the s relation or the tuple from the s relation will be subtracted from the old value on the joint relation in s and then can we have the new value. Next are the selection and the projection. Now if we made a selection on a particular part of that view, then we can update it as that means only the part of the relation R that we are making a selection and we are having that as a part of this old relation unioning it. So we can have the new relation. Now if we have selected a particular tuple or the set of values and then we want to delete it, then we can do it just like by subtracting the values. Next is the case of projection. Now projection is obviously much more difficult than selection. Say suppose we have a relation with VAR. Now we have a relation R on the sets of A and B. So the sets of A and B has two values, one is A2, another is A3. Now I want to project on A2. So if you delete this tuple A2, then we cannot have the projection pi AR on a particular attribute A because it will show an empty relation because this 2 is referring to both the A's here, because A is the attribute that we are choosing for the projection. Now, if one attribute we are choosing for projection that has got a relation with another attribute with two different values, and one of the values are deleted, then the projection will show empty, which is an error to us because it is containing the value A3. So if deleted the first entry to this particular attribute value, then it will consider the projection as empty for a materialized view. Because it is being viewed on a particular condition, so if we created the view like this, then it can have the duplicate values to it. So the projection will give us empty if we delete this operation, which is not desirable. So it can be removed, this discrepancy, by two ways. So we can delete one tuple from this relation. Other than having the projection on an attribute, we can just have delete the value from that tuple and then again update to our view. So it is quite difficult because deleting a tuple from a particular attribute value inside a view is not possible in some certain situations. So we need to make specify the situation first and then we have to perform their one. So there is no general rule for the projection on a particular operation if the deletion is mandated. Now the insertion is an easier one because we insert a particular value on the projected an attribute and we can add the new value to the relation. So one way is to possible remedy to this problem is if there is a deletion, say for an tuple tr and attribute value a. So every value of a that has got the same reference, that is for a2 and for a3, we will have one count variable associated with it. So whenever there is an entry in the view, we will add the count tr.a1. That means 1 will be added to the count so that we can see that if there is any count to that particular attribute value or not. So if the count is greater than 0, then we can specify that the tuple has got some reference with these attribute values which is still present in the view. Now for the deletion also, we will perform this count tr.a -1. That means when each will reach 0, we can say that there is no reference to that attribute and we can delete the reference. Now in this way we can somehow achieve a deletion or insertion in the projection operation. Next are the aggregation operation. To start with the aggregation operation, we will start with count. Now as the count is the view on this particular materialized one, that means the view has been now stored into the database. So any count that we are updating, we need to count it back to the result relation or not. So if it is the result relation that is being the update, then only we can perform the count. So we can allow an aggregation operation on count if and only if the B attribute is on A attribute on the addition. So if we are counting to it, that means we are counting the particular value B to it. So we are creating this view by having t.b, 1 to the function count. So now we will count more 1 to this t.b value. That means now we are counting a particular attribute and adding an 1 to it. So we can add an 2 and 3 to it as a specification to the materialized view. Now to delete this one, just we need to perform -1 or minus performance on that particular integer value. Next is the sum. Now sum is much more interesting on a projection or a selection on a particular relation that is being transferred to a materialized view. Say suppose that means we are adding some values to the attribute. That means we are adding the value of A to the attribute B. So if there is any insertion of IR to this V new, That means we are performing the summation of T dot A and T dot B to it. That means the first one is the attribute value that is to be added to the T dot B. So other than having an attribute value added to another attribute value, we can also add an integer to an attribute value. So we can also add like some T point A equals to 5. That means 5 will be added to the T dot A's value. Now, if the dr is the view that we are creating, and for deleting from the view, then we need to check that the view is again some aggregation function sum or not. So if it is some aggregation function sum that it is noting to, so we will first create to look up that if the t dot a is present or not. If it is present, then we need to look that it is associated to dr or not. If it is associated to dr, then we can perform the sum on it. So in this way, we can select a particular tuple based on a sum condition. Say suppose the sum of salary is 50,000, then delete the views of the particular relation. Next is the average. We just cannot perform directly any aggregation function average on a materialized view, because here the aggregate functions on average will have different types of attribute values which is not accommodated by the materialized view. So to perform this A average on a particular attribute B on a relation R, we need to perform the sum and the count on that particular relation, and then have sum divided by count as the average on that attribute. So we cannot use AVJ function directly onto the materialized view. Next are the mean and max. Say suppose from the total salary, I want to find from the view that which is the highest paid department and which is the lowest paid department. So we can directly use the mean and max on the salary, that is the total salary to the department group wise. So first we need to find this mean V new on IR. That means if there is any update, then we are finding the new value and the minimum of that new value that is being updated. So since the incremental view on maintenance, that means we are having some update to it. So it is not like the fetching of data, it is like the updation of the data. So if there are any insertion and we need to find the new inserted minimum value, then we have can IR, or if there is any deletion and after that we need to find a minimum value, then we can perform the same with the dr attribute. Now let us talk about the relational view or other operation on the set operations. So what happens in the set case? That if we have this R union S, then how it is updated on the view. Say suppose there is an update IR on a particular R relation which has an union with S, that is being the updated on view. So how can we update it? We just update that IR being union with R, and then it will be union with S as our new value. Now if there is any intersection, that means two relations are there and only intersected value, we need to add it to the new updated view. Then how can we have it? The R intersection S, let us take as an T, then the V new will be assigned to T union R union S. That means already R union S is there and we are adding the T as the intersection to R union S to an updated view. Now if we internally update a view like E1 join E2. Now if there is an update I1 that belongs to E1 and there is an update I2 that belongs to E2. So what will happen in case of the materialized view? We will have first we need to join the value from the internal update with the VOLT and same with the E2 to the VOLT. Finally these two joining will then assign to my v new. Now the same in the case of deletion. Say if the deletion is from a particular tuple set from a relation E1, then we have that update on the D1. So now we have incremented and finally we had this D1 joined with E1 so that we can have this V old, that is the previous value, and if you subtract this one, that means the join D1 with this E1 relation which belongs to this R, so we can have our V new that is attached to it. Now let us consider the materialized view for the selection and the projection operation. Now suppose we have a view that is a selection of theta predicate on relation R. Now suppose that we want to update our view so that we can I tuples that is attached with this view. So now we can have this selection modified by this IR as with this view, which we can write like. So now the previous value which was holding this selection of R, now we have the previous value and also with the insertion that we need to make first to the relation R, and then we need to select the same predicate so that one can have our view as our V new. Now the same update if we perform it by deleting, then we can have it like if the DR number of relation that need to be deleted from the view. So the first it need to be deleted from the relation and then we have selected from the deletion and then we can add it to our V old. Or here we can subtract it from the V old, so have the V new as the new deleted rows from the new view. Now the projection is a little much more difficult because now the projection needs that a particular value that we need to project on the values that have selected. Say suppose that an attribute has two values that is associated to it at two instances of time. Now how can we project at this materialized view, that means which keep updating from time to time. Say for instance we have an V which is a projection of variable A on this relation R. Now we have this modification. Now we can see that it is the A2 and A3 that is associated with the relation AB value. Say suppose that the attribute is getting this A on this relation R. So now we can have only one tuple that is associated with A in this view because it's a projection on the attribute A. Now suppose that we want to delete this A2 here. So what happens, we cannot just delete this A from our projection R, otherwise it will be an empty relation because it is having only A2, not both A2 and A3. So that is the problem with the delete with the projection in a materialized view. So how I can delete a particular tuple from a materialized view which has two values on other attributes that is associated with the relation. So we first need T dot A in each of this V. Then we have the delete on this V new as the V old will be the deletion of this tuple T dot A, not A. So now we can have, so how we can calculate this tuple has got one value or not? We associated with each attribute that the values on the other attributes which is dependent on it. If it has got more than one, then we introduce another variable count which just count this T dot A. So we can only delete a value from the view as well as from the relation if the T dot A is equals to 0. And if it is greater than 0, then we cannot delete the value as there are only associated value in the view but also many associated values in the relation. So the delete will give an inconsistent and also an empty view which we cannot relate with the relation. So that is the projection operation then which I can deal with this selection one and the deletion and the insertion one. Now consider the aggregate function that we can perform on this materialized view. First one is the count function. Say we have the count option for this grouping by A, then we are counting this B. So how we can do that inside the view? So for every associated value, we first need to add and find all this T dot A that we have calculated for the deletion. Now we add if this t dot a comma 1 for each value b that is not belonging to the relation R or the V of R. That means if the value is not present in V, then first we add every t dot a that has an associated value with b. And now we can perform the count option on this b so that we can have calculated all the values that is associated with attribute b. Now if we had this t dot a equals to 0, then we can say that there is no values associated to it, and we can just delete this attribute or from the view this tuple, because we are not having this anymore in the relation. Now the next one is the sum. See, it's the same example that we are having, that we are grouping a value by attribute A and then we are summing that with B on a relation R. So what we can do, we can find all this t dot a that belongs to the view and also the t dot b that belongs to this v. Now we will find this t dot b and again the t dot b for each of these values. So for the second one we will plus 1 and plus 1 it with if we have more than 2 values that is associated to it. And finally we will perform this add t dot a and t dot b so that we can add the values of a and b on this view that belongs to the relational attribute. Next one is then AVG. Now the AVG cannot be performed directly in the materialized views because we cannot have the option average to be calculated if one value is associated with more than one value. So just like the previous one, if we need to calculate the V that is grouped on A and then we need to calculate the AVJ of B on relation R, then we can find the sum of R and then we can have the count of R so that we have the number of that particular value. So we will have this average on R performed in this way on the materialized views. Next is the min max option. The min max option is very easy. We need to find the TA and then we can find all the minimum values and maximum values that is associated with the attribute. Now the other operations like the set differences, we can have performed this R intersection S and then we can perform R minus R intersection S so that we can have this R minus S. So in this way we can perform all this materialized view options that we can provide with the relation. Now how can we handle this expression? Say suppose that we have joined E1 with E2. And now we are having one value that is associated only with E1, that is I1 that is associated with E1. And if we want to perform this E1 to E2, so first we can have this I1 to E1. That means we are having this D1 that is having this I1 joining E1. And now if we perform this D1 join with E2, then we can have E1 join with E2. So first it is happened in the relational level and then we can have that particular relational join with other relation to maintain this expression. So how can we perform the query optimization on this materialized view? Say suppose the first one is rewriting the query. We have to need to R join S join T and we have already the view that is join on R on S. So we can just rewrite the query by V join T so that we can achieve our R join S join T. Next, the next one is replacing. Say suppose that we have R join S as a view. Now there is no index that is maintained on this view and now we want to select a predicate that is A equals to 10 on V. And now my A that belongs to relation R. So now how can we perform this one? We can replace this query by having the selection A equals to 10 be made on R and then we can join this with relation S. So now the optimized query will be less costly and it will be obviously effective more than the previous one. So we can done with either rewriting the query or replacing the query within smaller version equivalent expression. Now the problem of this index selection that we have, say suppose that we are having a equals to 10 and we have also an b that belongs to s. So if there is a equals to 10 and b equals to 5 that we need to perform on v, then we can join it by selecting the proper indices, right? So here we need to select the first index on each of this relation so that we can arrive with a workload that is associated with the materialized view. So if the workload is high, then we need to break it to smaller parts so that we can achieve it more faster. Now the materialized view is extremely important and necessary to take care with, because now we can have all the selection and projection operation and also the min max, the count, like this aggregate operation to be performed on it based on the counter that will count every tuple which has an associated value of one attribute with other in the relation. So now accordingly we need to maintain the relation too. So that is all for the materialized view for this query processing and optimization. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.